Hi, welcome back. Today we're going to talk about derivatives, what they are, and certain algorithms to calculate them. So we've kind of already covered on this about the fact that a derivative is finding the instantaneous rate of change at any given point on some function f of x. And we were able to calculate in the last video that to find the change in y over change in x, we can take f of x plus some value h, so we're moving forward on the x-axis, minus f of just f of x, and so that's going to give us the height of the graph, and then h is going to be the width of that triangle. And the idea is that the closer the h gets to 0, so we make it infinitesimally small, all of a sudden we get a perfect rate of change for that point. So if h is any actual number, then we're just looking at an approximation. But as h approaches 0, the approximation approaches perfection. So this is the definition, you could call it. This is the thing that proves what a derivative is. But luckily for us, because sometimes these limits can be tricky, luckily for us, a lot of people worked on finding algorithms for calculating derivatives. And there are several algorithms. There is the power rule. Then there is the product rule. The quotient rule, and the chain rule. And these are the four major algorithms that help us to calculate derivatives. And armed with these four, you'll be able to handle any sort of polynomial that's non-trigonometric, or even polynomials that are, even things that aren't necessarily polynomials, as long as there's no trigonometrics in there. There are going to be several trigonometric rules that mainly just have to be memorized, or in your class you're provided a table of derivatives that you can use to help yourself during a test or homework. So these are the four major rules, and I'm just going to focus on the power rule right now, and perhaps the product rule as well. Well, let's just focus on the power rule. I'll do the product and quotient in the next video. So what the power rule says is that if you have some function of x equal to, let's say, x cubed, that the derivative f prime of x, so that is our shorthand for writing the derivative of f of x. What we do is we bring down the 3 from the power up here, and we bring it to the front of the x. And then we subtract 1 from the power. So 3 minus 1 is 2. And that's an example of the power rule. Now there is a more general way to write this, and how we would do that is if we said f of x is equal to, let's say, x to the n, so n could be any number, well then f prime of x would be equal to n times x to the power of n minus 1. So just like up here, n was 3, we brought n to the front, and then we subtracted 1 from the n. Now another thing that's important to know with derivatives is something called linearity. And because derivatives are a linear function, that means you can apply linearity. And what that means is, for example, if I have f of x and it's a polynomial, like 3x squared plus 2x plus 5. So if I want to take the derivative of this, f prime of x is going to equal to d dx, and of course d dx stands for the derivative with respect to x. And that's a more way to write it as opposed to prime. But prime will save you a lot of time. So this is the derivative we have to take. Well, applying linearity means that we can separate each term and take the derivatives of each term individually. That's one of the definitions of a linear operator. So I can now take the derivative with respect to x of 3x squared plus the derivative with respect to x of 2x plus the derivative with respect to x of 5. Another beautiful thing about derivatives, because they're a linear operator, is you can pull out the constants. So the constants, if you pull them out and multiply them back in, it actually does not make a difference on a process. So I could write this as 3 d dx of x squared plus 2 derivative with respect to x of x, and then plus 5 derivative with respect to x of 1. Now, another thing about the power rule is that the format, so remember we were saying that it's to find the derivative of x to the n, that's going to equal n times x to the n minus 1. Well, what if n is 0? Well, if n is 0, then we end up with a constant. Anything to the power of 0 is 1. Well, this rule doesn't really apply there. When we get down to the constant level, we actually, the derivative of a constant is 0. And I'll tell you why, because a constant, if we were to graph out a constant, like say y equals 1, that's a line that looks like this. Well, what is its rate of change? It's not, well, firstly, it's not changing at all. Secondly, its slope is 0. And so the slope of any constant is going to be 0 because any constant graphed out is going to be a flat line. And so that's why the derivative of constants are 0. Now let's look at something linear like the x here. So x, if we were to graph x, is going to be a point slope line that we would indicate, with y equals mx plus b. You'll notice something is that the rate of change along this line doesn't change. It always has the same slope. And so if we want to take the derivative with respect to x of, say, 2x, its slope is 2. So its rate of change is always 2. And so so if you take the derivative of a constant at 0, if you take the derivative of, say, like 2x, the derivative of that is 2. So the x goes away, the slope stays. And then we'll go ahead and finish this problem. So x squared, the derivative of x squared is 2x, and we still have 3 on the outside here. The derivative of x is 1, and we still have 2 hanging out here. And the derivative of 1 is 0, and 0 times 5 is also 0. So we've now solved the derivative. It's 6x plus 2 for this particular function that we made up. So that's the power rule. Derivatives of constants are 0. Derivatives of, like, say, 2x is just 2. The derivative of any number n, so nx, the derivative of any number nx with respect to x is just n. So whatever number was in front of the x is all that's left after we take the derivative. Alright, so that is the power rule, and next video we're going to talk about the product and the quotient rule, because they're kind of two sides of the same coin. And so I hope you have a great day, and I'll see you next time.